All right, so chapter 5 is basically about how forensic scientists use properties of matter and some physics properties like light and reflection to analyze things like glass. So this is the broken glass unit. Someone mentioned that we have enough broken glass in here, so it shouldn't be an issue. I know, right? So we'll look at some of the properties of matter. So properties of matter, they're going to forensic scientists use properties of matter because these are the distinguishing characteristics of a substance. It can be physical, they can be chemical, they can be intensive, and they can be extensive. This idea of intensive and extensive is not expressly written in your textbook. It's one of those things that is implied that you should know, so previous knowledge. So for a physical property, it's describing a substance without changing the composition. So it makes no reference to another substance is the way in which your book describes it. In chemistry, we always said that it can be observed with the 5 senses. So what are the 5 senses? Okay, so we have sight, smell, sound, taste, and 1, 2, 3, 4, touch. Now, I guess technically there are like 6, like umami, but we won't be using that. I know we won't be using that in here. And we always say, which are the ones that we use most often to make observations? Sight. What else? Smell sometimes, sound. We tend not to use taste or touch. An example where you could use touch here would be whether or not something would be endothermic or exothermic, meaning like if the container got cold, it would be endothermic. If the container got warm, it would be exothermic. When we smell things in the lab, how do we smell them? We waft them. You don't put your nose directly to the odor. You let the smell come to you, like when someone crop dusts in the grocery store, right? Yeah, you don't even have to waft it. The smell will come to you. You don't put it on the source. Sound is definitely an observation that we can make in the lab. You might hear it bubbling. You might hear it fizzing. You might hear, yes, when we would light the hydrogen gas during the chemical and physical properties lab. I barked like a dog every time it happened. It can be chemical. So a chemical property describes the behavior of a substance when it reacts or combines with another substance. In chemistry class, we said this is going to be a change in the composition. So this is generally something that if you try to test a physical or a chemical property rather, you're not going to be able to go back. You're going to change the composition of the substance. So something like it burns. And usually when they say something burns, it burns in the presence of oxygen or burns in air. It might react with hydrochloric acid. So you could things like flammability, reactivity. These are chemical properties. We're going to do a lab because that's what we do, and it's going to be the identification of unknown white powders. Yesterday, Trump's daughter-in-law she opened a letter that contained an unknown white powder, and then she said she felt sick, although the powder was shown to be non-toxic, so it was probably psychosomatic, so they took the 3 individuals who were with her when she opened the letter to the hospital as a precaution. It could have been cornstarch. But to be honest with you, any white powder inhaled can be deadly if it sticks to your alveoli and you can no longer have gas exchange. So we're going to be utilizing these ideas of chemical and physical properties to help you identify unknown white powders. Properties can also be intensive or extensive. This is, again, something that's implied that you should understand that's not expressly written in your book. So an intensive property is a property that it can be either chemical or physical, but it's unique to a substance, meaning that we can use it to identify something. It's always easy to remember intensive, identify, they both start with an I. So for example, density at a certain temperature is an intensive property. I know that water at 22 degrees Celsius has a density of 1.0 grams per milliliter. So if I had 2 clear liquids and I checked their density, if one was found to be 1.0 and the other one was found to be 0.85, I would be able to tell which one is the water and which one would be alcohol. Melting point is another intensive property. It's unique to a substance. Boiling point, specific heat capacity, color, these are all examples of intensive properties. Density, is that going to be a physical or a chemical property? Physical, I'm not going to change the composition of my chemical substance if I look for the density. By the way, what is density? Because you're going to have to use it later on in the unit. Mass over volume, perfect. Melting point, is that going to be a chemical or physical property? Physical, very good. What about boiling point? Physical. Specific heat? What's specific heat capacity?
The amount of energy required to raise 1 mole.
Not 1 mole. 1 gram by 1 degree Celsius. Very good. That's also a physical property. Color is going to be a physical property as well. It can be extensive. An extensive property, it can be either chemical or physical, but it's a property that is dependent upon the quantity of the substance that you have. So for example, mass or volume. Both physical properties, they're extensive. I could tell you I have 40 grams. I have 40 grams of what? You don't know. It doesn't help you identify the substance. Well, I know what you got 40 grams of. I have 591 milliliters. Doesn't tell you exactly what I have. But you all know. So, on page 145 in your textbook is the SI system and the metric equivalents. Please be able to do the conversions. Oh yes. This is a basic math skill that you should know. Basic math. So, it wants to, first of all, the SI units. Why do we use the SI units or the metric system in science? Well, it's the System International. I don't speak French either. But it's what is used throughout the world. So it's a universal system. Why do we use that as opposed to the American conventions for measurements?
We're the only ones.
We are not the only ones. There are 2 other locations that utilize it as well.
But like, it's fractions. Like, it sucks.
Well, the metric system is based.
Perfect. Because the metric system is based on units of 10. So it's much easier to do your conversions.
So why Americans?
Why do Americans not use it? Come on now. We're special. You're also required to know the SI units for length, mass, volume, distance. So what is the SI unit for length? Meters. Very good. What about for mass? It is not gram. It's kilogram. Very good. The SI unit for mass is kilogram. It's the only one that's going to use the prefix. What about volume? Well, volume for a solid would be meters cubed. For a liquid would be liters. And what?
No, I'm just saying I still can't convert liters into gallons.
Oh, convert liters to gallons? Yeah. You'd have, no, it's really weird. I don't know that one by heart. I have to go through like smaller increments. I actually, you know what I have to do? I go from liters to milliliters to grams and gram. I go all the way through that way. What about distance? It's meters. So when you do measurements in here, especially in this unit, you're going to make sure that you're using these SI units. When they tell you to be able to do the conversions, it's basically the old King Henry died by drinking chocolate milk. So if you don't know that, in the middle you'd have your base unit. So this is going to be things like meters, grams, liters. Those are your bases. In a whole number, where do you find the decimal point? So if I have this number here, where's the decimal point? At the end. So when you do conversions like this, the little d stands for deci. The little c is centi. This is milli. The big D is deca, hecta, and kilo. Capital D. So if I have 3 meters and I asked you how many milliliters or millimeters it is, there's 2 ways you can do it. You can do it simple dimensional analysis, or you can do, sorry, Rebecca, or you can just move the decimal. So for example, you told me that the decimal at the end of my 3 meters is at the end of the number. So meters is my base. I'm going to put my decimal right there. I'm going to go to the milli. So I go 1, 2, 3. I move my decimal 3 places. So I'm going to do the same thing here. 1, 2, 3. And then I just fill it in with zeros. So 3 meters is 3,000 millimeters. Basic metric conversions. Yes. That was this year too, at the beginning of the year. Basic review. And remember that a century has 100 years in it, so a centimeter is 100. 100 centimeters is 1 meter. So again, I would look on page 145, 146, it carries over onto if you don't know or are not comfortable with your SI units and your metric conversions. Then it goes into a review of, in order to understand the basic properties of matter, forensic scientists must understand the basics of matter. So what is matter? Yep, anything that has mass and takes up space. So mass and takes up space, which is volume. So how is matter classified? Yes. So matter can be classified, remember your flow chart? Let's see. Yeah, I know. So for matter, if we have matter, anything that has mass and takes up space, the first question you have to ask yourself is, can it be perfect, physically separated? Give me an example of a physical separation technique. Straining, so filtration. Yep, straining. Chromatography is another one. Distillation. These are all physical separation techniques. I mean, if you look at boiled spaghetti and water using the colander, that's a physical separation technique. If it can be physically separated, what is it? It is a mixture. Right? If it cannot be physically separated, what is it? It is a pure substance. So for pure substances, what's the next question you have to ask yourself? Can it be chemically separated? An example of a chemical separation would be electrolysis. Adding a current of electricity into a container of water can cause it to separate into hydrogen gas and oxygen gas. So if it can be chemically separated, what is it? It's a compound. Now we're going to talk about this in a second. Your book uses compound and molecule almost interchangeably. Drives me up a wall. What if we cannot physically separate it or chemically separate it? It's going to be an element. So your two options for pure substances are going to be elements and compounds. Give me an example of an element. Oxygen, gold. So an element, by definition, is what? It's on the periodic table. They consider the elements to be the building blocks of all matter. They are on the periodic table. And so an example, I'm just going to write down like carbon. What about a compound? A compound is going to be two or more elements together. Give me an example. Sure, NaCl. We're talking a second to remind you that the properties of a compound are different than the constituent parts. What about your mixtures? What's the next question we have to ask ourselves? Is it uniform? What if it's not? It's heterogeneous. All right, if it's heterogeneous or heterogeneous, we had two options. Do you remember what they were? Suspension. Remember, a colloid is where the particles look uniform, so the particle size is so small that it appears to be uniform throughout. So an example of that would be like fog or milk. And it shows us what we call the Tyndall effect. Suspensions, on the other hand, this is where you have clearly separate, you can see the different pieces in it. So like an example would be a chocolate chip cookie or Italian salad dressing. What if it is uniform throughout? Then it's going to be homogeneous. And examples of things that are homogeneous would be aqueous solutions, alloys. Air is always an example. What's an alloy? It's going to be a mixture of metals. Give me an example. Brass, classic one. Pewter. No, I think pewter is more of a patina that's put on, that's like, it's the film on the copper from oxidation, I believe. So when you go through, oh. That's a ton of things in that alloy. So that's how you're going to be able to break down matter. Your book spends a lot of time talking about suspensions. So your book spends a lot of time talking about suspensions. It's important to know that sometimes they will mix things together just to see how they settle out. Which means that you're going to have to use the periodic table in this unit. So, what is the periodic table? The periodic table it's basically a chart of the known elements. And they're arranged systematically. How are they arranged systematically? Well, it's the increasing atomic number. The atomic number is the same as the number of protons. It's also going to be arranged in increasing energy levels. As well as increasing mass. Because we're talking about the properties of elements, it's important to understand how the arrangement of the periodic table can help you to construe or to kind of figure out the relationship of properties. Sorry. So what do we call on the periodic table? Going up and down. What are these called? It's either going to be a family or a group. You can remember that your family or your group will always stand up for you. Then going across this way, what is that called? That is your period. Because when you're on your period, you want to lay down? Okay. So, periodic tables arranged in families or groups and then periods as well. Elements in the same family have similar properties. So, same family equals same or similar properties. Why? Very good. What's a valence electron, Madeline? Outermost. Very good. So they have very predictable trends as you go up or down a group. For example, when you go down the noble gases on the end, you know that their mass increases, which means that they're more polarizable, so they're going to have stronger intermolecular forces. Same thing with your halogens. Because I know that, I can make the assumption that bromine is a liquid and iodine is a solid. Because I know that as they go down the periodic table, that they're getting larger. Because they're getting larger, they're more polarizable. Because they're more polarizable, they have stronger London dispersion forces. And those stronger intermolecular forces are more difficult to overcome, thereby causing the different changes of state. Going across the period can provide clues to behavior as well. For example, anything that is in this middle section here going across, those are going to be metals. The elements all have letters. They're letters, we call them their symbols. And they're either going to come from English, Latin, or Greek. Just so you know, if you looked on the periodic table, for example, if you looked at carbon, you would see something like this. This number on the top is your atomic number. It's equal to the number of protons. The bottom is the average atomic mass. It comes from a weighted average of all naturally occurring isotopes, and this would be the symbol. What? So when two or more elements combine, they form compounds. Your book refers to as molecules. It drives me up a wall. Your book differentiates between a molecule and a compound by stating that a molecule is the smallest unit of a compound that still retains the properties of that compound. So they call a molecule the smallest unit of a compound. That still retains those properties. What is the smallest unit of an element that retains the properties? So the atoms are the smallest unit of an element that still make up those properties. What that means is I can have one atom of aluminum and it's still going to have the same properties and behaviors of aluminum. But if I break it down into the protons, neutrons, and electrons, it no longer has those same properties. It's important to remember properties of a compound are different from that of the individual elements that make it up. For example, NaCl is table salt. It's a solid at room temperature. It's very brittle. It kind of looks like glass. It's crystalline. But sodium at room temperature is a soft, flammable metal. Chlorine is a green, poisonous gas. Together, they make up innocuous table salt that you would use to salt your food. So the parts of it have properties different from the compound. Yes?
What form of chlorine do they use for first? What is that?
It's usually sodium hypochlorite. You know, it's got other stuff in it. They call it chlorine because that's the part that you're looking for or that you're using, but it's not the same. There was actually a woman who basically made homemade bleach and was feeding it to her child with autism to cure him, because she found the recipe online, because it's like miracle mineral something, and she was giving it to her child until the father realized what was going on. No. What does the formula of a substance tell you? So if I have CO2, what does that tell you about it? 1 carbon, 2 oxygens. Now, I know most of you know this, but again, there are some people who do not, who have not had the class. So 1 carbon bonded to 2 oxygens. So the subscripts tell you the number of atoms. The symbol tells you the name of it. So the states of matter, there are means to classify the matter based on its physical form it takes. So basically there are 4 physical states of matter. Only 3 are generally used to classify. So what are your 4 states of matter? We're going to do solid, liquid, gas, and plasma. For plasma, we'll start with plasma. Plasma is going to be an ionized gas with equal number of cations and anions. What's a cation? Anions. Yep. So equal number of cations and anions. Plasma is, the property of plasma is different from regular gases, so they're considered to be a 4th state of matter. This is over 99% of the known universe is made up of plasma. However, we never talk about it, we never use it. So some examples of plasma, of course, is going to be what? Stars, the sun, lightning, welding arc. If you weld, the welding arc is plasma. The aurora borealis. Those are all examples of plasma. So the more innocuous states of matter, solid, liquid, and gas. Solid. These have strong intermolecular forces. Hold the particles tightly together. They tend to be rigid. They have a definite shape and volume. And the atoms or particles vibrate in place. They vacillate. Oscillate, vacillate. Yep, they're going to kind of go back and forth. They're going to move back and forth in place. So they're going to vibrate in place. So even though it looks like your desk, bless you, is stationary, those particles are still moving. Your liquids. Liquids are going to have intermolecular forces holding those molecules together, are not as strong as solids. As a result, the particles can flow past one another. That's why liquid is considered to be a fluid. Those particles move freely. They have a definite volume, but they take the shape of the container. I have 591 milliliters of Diet Dr. Pepper. Right now it's in the shape of a 20-ounce bottle. When I drink the entire thing, it will have the shape of my stomach, but it will still be 591 milliliters. And finally, gases. Gases have the weakest intermolecular forces. The attractive forces are actually less than the force generated by the kinetic energy by the movement of the particles. That's why they're able to move around freely. So the kinetic energy is greater than that of the force of attraction between them. So the particles move freely and very rapidly. They have no definite shape, no defined volume. They are compressible. And these are also considered to be a fluid because the particles are able to move around one another. One of the most important physical properties are going to be between changes of state. So changes of state occur when a substance goes from one state of matter to the other one. The change does not change the chemical composition, but only overcomes those intermolecular attractions that are holding the molecules together or the particles together. As a result, changes of state are physical properties. Physical changes can be used as a physical property. An example would be ice going into water, turning into water vapor. In order for me to go from ice to water vapor, what has to happen? If I increase the temperature, I'm adding energy. That energy goes to breaking those intermolecular forces. So if I have a water molecule here, and I've got another water molecule here, in between them is the intermolecular force, the hydrogen bond. When I go from water to water vapor, what am I breaking? I'm breaking this, not this. So I'm going from, it's still going to have the same chemical composition. It's still going to be 2 hydrogens bonded to 1 oxygen. It's not going to be just hydrogen and oxygen. So what are the phase changes? Well, you used to know the phase change triangle.
Oh, sublimation.
Sublimation. So instead, we're going to add the plasma to it. When we go from, let's start easy. When we go solid to a liquid, what is that?
Solid to a liquid vapor.
That's melting. Ooh. What about when you go from a liquid to a solid? Freezing. I like when some people can't remember freezing and they write solidification.
What?
Good one. Oh, she looks pretty.
No, I'm not looking at you. I'm looking at whatever Jenny's doing. It's not paying attention. That's okay. I've learned not to be offended by when Jenny doesn't pay attention to me. From liquid to a gas, what is that? That is vaporization, not evaporation. Evaporation is a special type of vaporization. Gas to a liquid? Condensation, that's what happens on your bathroom mirror when you take a really long hot shower. All right, gas or solid to a gas.
That's sublimation.
That's sublimation.
And the other way is deposition.
And the other way is deposition. Give me an example of deposition. Frost on your window in the wintertime. Gas to plasma.
Ooh, we don't know that.
It's ionization.
Deionization.
It is not deionization. Going from plasma to a gas is called recombination. And that